Okay, so this is kicking into chapter 8, which is all about polymorphism. This is actually a really important topic. I'm not sure if at this point in the semester, if you're connecting with the relative value, the deeper understanding of types, understanding the whole linkage process and, getting a little bit into thinking in a functional language like ML. I hope you are, but polymorphism is a really, really important topic when you're trying to understand programming languages. And that's really the focus of Chapter 8. Chapter 8 is not that big. What is it? It's just, it's like 12 pages or something. And the concepts are pretty powerful and it's a little bit dense. And so I want to try to break it down for you and walk through it. But I think you'll get this if you can kind of just get past some of the syntactic junk that we have to kind of wade through to get there. I think it's going to make a lot of sense for you. So, um, the first thing, I guess, kind of by way of introduction, in this example at the top here, right, we've got an example in C, and then at the bottom we got an example in ML. Okay, and so let's just kind of break down that again. I'm not sure how fresh you are on your C syntax, right? But basically, what you're doing, you're declaring a function called f, and then it's going to take a character called a and another character type b as its parameters. It's going to return an integer back out, and then inside the body of the function defined by the brackets, you got return, and then it makes a comparison of a equal to b, and then it's going to return that as an integer. Okay, that is an equivalence, right? Is a equal to b. In C, you've got a certain kind of flexibility, for example, doing comparisons, and having, the notion of a Boolean value is essentially an integer that can be zero or non-zero, basically. Anyway, that's a little funky, but you kind of just sort of see this idea. Down here in ML, we have, remember that types are so important in ML that it always tells you what the type is of everything you define, right? And so in this case, remember that's the ML prompt. So we're typing function, fun. I got f, I want to take an a and a b, and I'm going to return, right? And that's going to be defined as this expression. And that expression, a equals b in parens, is a comparison. It's just a Boolean value. And then what's cool, of course, is that ML then turns around and tells you, oh, the value of f is a function. And that function, the type definition is that it'll take anything, it'll make a tuple out of anything and anything, okay? And it's going to return a Boolean. And it tells me that, okay? And this anything is really a powerful concept. And really, truly, most languages don't give you that. Just like built in. They often give you the ability to go there, but with a lot of work and a lot of heavy lifting and dunging around in the background, and but very few. I don't even know if I've ever seen a language as flexible as ML in the sense of, as long as you're consistent, I don't care what you're doing or what type it is. That's actually very powerful and very cool. The rest of them, like again, back to this example, I got to go, that's an integer, that's a character, that's a character, stuff like that. And a little bit of flex on some things, but it's pretty tight. And so when we have these functions that, or really, well, we're going to talk about the fact that it's a difficult word to define, right? But when we deal with functions, let's say, that have a real great flexibility with respect to type, we call that polymorphism. And polymorphism being a fancy word, it comes from like Greek, I think, but I think he actually talks about it in the book, like where it comes from. But Greek meaning many forms. There you go. So polymorphic basically just means I can do this thing for a lot of different types, is usually when we talk about polymorphism. We're talking about flexibility with respect to types. But it's become, it's something that gets used a lot in a lot of different ways. And so we're going to kind of walk through, these main ones. What I'm going to do in this podcast is hit overloading and then bust out these others into individual podcasts so that you've got smaller bite sizes. Okay. All right, so let's talk about overloading, which I'm glad it's first because I think it's most important, and I think that it is a very common concept. It has become increasingly common, okay, over time. And the notion of an overloaded function name or an overloaded operator is that you've got multiple definitions for the same thing, and that's a little bit non-intuitive out of the chute, right? When you think about it. Um, and I would just hit this last bullet before I jump on to the next slide where we kind of show you some examples. But this last one actually points out that in some languages you can roll your own. So in other words, in some languages there is a set of overloaded operators or functions, and which is not uncommon in probably most languages. And then there's some languages like C++ that lets you create new overloaded function names and operators of your own design. And they can kind of mean whatever you want them to mean, which is fairly cool. Although, it's kind of like, it's almost like it's programming tricks, right? It's like creating new language features that I just want to have there. And then I build those in, and then having created those overloaded operators, I can now go write code a lot easier than I would otherwise have to do it. That's bottom line. Um, all right, so here's an example. The top one is ML, the bottom one is Pascal. I want to just say that Pascal, I remember this, that you could concatenate strings with the plus sign, right? That's clearly an integer, right? A's got integers, B's got real numbers, C's got strings, D's got, like, I think that's if I'm remembering correctly, I think that's an enumerated type that goes from A to D, and then I can just tack on F and into that. So I've got a lot of flexibility, and these are built-ins. My recollection from Pascal was that you couldn't define your own, but that there was this set of these. In ML, I've got the plus operator as well, overloaded for both integers and reals, but I don't believe it's overloaded for anything else beyond that, okay? Now you get to something like C++, and it gives you actually quite a bit of power. But I want to just point out here for a second. Let's go back, all right? Okay, where is it? Yeah, right here, right? Remember this guy here? I've got yeah, a little bit of junk here, but over here in ML, it's pretty straightforward, right? I defined that. And it's like, yeah, whatever you want to throw in there, man, as long as it's a tuple. I don't care, tuple of ints, tuple of whatever, right? Then I'm good. And I'm going to return back a Boolean. And it's just tremendously flexible. Sorry, moving forward again, back where we were. Okay, to do stuff like that in C++, you're into this kind of crap. You got all this junk that you got to do. So, and then you got it, but you got to do all this junk. That's the problem, right? So let me just kind of walk through this a little bit. This is a class definition up here, okay? This top half is a class definition. The bottom half is actually just defining a function that uses it. Okay, so ignore the bottom for now. So the top part defines a class called complex. And what it's trying to do, one of those very mathy examples, right, which some of you will dig and some of you will not dig, which is a complex number is one that has a real number and an imaginary number, I don't know, what are those imaginary numbers, the square root of -1, stuff like that. And so it creates, it has a data space, which is RP and IP, which is real part and imaginary part. They're both doubles. And then it defines these methods. Okay, well this one's the constructor, and it's a parameterized constructor. So when I launch this thing, I can put those numbers in there. Okay. And then basically what happens is I take I and I put that into the I part, and I take R and I put that into the R part. Okay, that's what happens when this constructor gets called. Then over here on this next part, this is key. That's the keyword right there. Operator plus, operator star, and those allow me to overload the plus and the star, operator. And complex is the type. So I'm basically defining. I'm not actually writing the code for it here. It's going to be elsewhere, but I'm going to go ahead and define basically essentially it's my magic way in C++ of saying the plus operator, and it's going to have two complexes as parameters, right? Which is going to be parameters. Sorry. It's going to be two complex numbers as parameters to the plus operator, okay? And then it's going to have two complex numbers as parameters to the star operator, okay? And then the way that's going to work inside the syntactic space of C++, of course, is it's going to be this guy plus that guy, this guy times that guy, because the syntax is going to work out. And then all friend does basically is says that this stuff is defined, sort of elsewhere, but is allowed access to everything. So I can see all the private space inside here, but otherwise it's visible, outside and defined externally, right? And then finally, this is my definition of a function called f. The return value is of type void, which means it doesn't have anything coming back out. And then it's going to take as parameters coming in three complex numbers that are just called a, b, and c. And then it's going to, what this does is defines a variable d of type complex. Then it performs this a plus b times c, performs that operation, and shoves that value into d. Okay. So again, that's a lot of words to just sort of say, I want this to work. I want pluses to work differently. It's a bit of work, right? But you can see that I can do it in C++. And then the funky paradox is that, and then what I get is other features that I can use when I'm writing my code. So that's cool. So kind of continuing, basically C++ says that all the operators can basically be overloaded. I can redo all of them for my own types, whatever it is I want to do. And that includes, like, look at those, like plus, minus, times, divide, all of them. And I can decide what they mean to fit my purposes. I can even overload new and delete, which are the allocation and deallocation things for memory management. I can overload function call. I can overload the subscripts and have that mean, something different. Anyway, it's crazy. It's a little crazy. It gets a little bit insane, okay? But there you have it. And then also in C++, I mean, you can see again a lot of the power, right, of C++. But also in C++, I can overload function names, right? So check this out. And this part is a little bit funky, a little bit tricky, but really, really important. And I want you to understand this. So what you've got here is a function called square, right? And it's taking an x as a parameter. It's gonna square it. It's gonna multiply it times itself and return that. And there's the int that it expects. So it takes an int as an input, takes an int as an output, right? And then I've got a thing called square also, but this square, it takes a double as its input and returns a double as its output. And you're like, okay, what gives? Okay, so here's the key, and we're going to start. I'm gonna apologize for a little bit of the pedagogy in the next slide, because this sounds like, okay, why are we suddenly talking about how to eliminate it? Okay, well, this is important to lay a foundation for kind of what comes next. Okay, so if you were going to eliminate overloading and say, well, I don't want to use the same, I don't want to go square and square, it's too confusing. Well, I could just call that guy square I, and I could call this guy square D, right? And now they have unique names, and and that's fine. And then I could say that int a equals square I, right, with 3. If I'm going to the next one, right? So that guy becomes square I square D. And I just call square I square D. All right, I can do that. But it's just kind of clunky, right? I don't want to have to think about that. I want to be able to do this. I can just go in square, and as long as it's a squareable type, right? Meaning that I've defined a square with those types. That's how I know that this is okay. Remember in ML where we had certain types that were comparable, right? Like integers, and then other types that weren't comparable, like reals. Well, okay. If I do all that, I get what I'm basically doing is I'm disambiguating these things. So I don't have to worry about which one's which square. I know which one, and I have to call it explicitly, right? Well, basically, the reason that we kind of show that is to kind of just illustrate that compilers basically do that underneath. They do it behind the scenes, okay? And that's a little bit of a pulling the curtain away a little bit to show you a little bit what actually goes on there. So um, basically, what happens is here they invent a mangled name, okay? Which means that you see square in the code. Like let's go back one. You say you've got, let me go back again. Like that guy right there, right? I got an integer a, he's equal to the square of 3. As he's that square, we just look at it and go square. The compiler down underneath is going to do something like square I. And down here, something like square d. Something underneath that when you're down inside underneath and you're linking, you got to bring in a linkage to, these can't be the same code, right? Do you see what I'm trying to say? The code on the back end can't be the same. It has to be different because you don't deal with these things the same. But the code on the front end that I see looks the same, but when I compile it, it's going to actually reference two different, these two different functions, okay? And it's going to give them mangled names down, down behind the scenes. That's the point. And then when I'm actually, compiling and then linking and doing all that stuff, then I'm using the appropriate mangled name at that point, okay? All right, and then when this says monomorphic, all that means, it's the opposite of polymorphic. It means monomorphic functions mean I've got a square that only works on ints. I got a square that only works on doubles, right? Stuff like that. And then here's kind of an example. We have this thing called, this is C++, right? So I've got a function called Shazam, and it takes two integers, and it returns an integer, and that's its sort of that's its definition of the function, a plus b. That's Shazam. And then I've got this other Shazam, which takes two doubles and returns a double, right? And it returns a plus b. Okay, let's for a second ignore the fact that we've got overloaded plus signs here. Ignore that for now. We're talking about this right here, Shazam. Okay, so underneath, if you look at what's happening in the assembler, this guy's going to be Shazam underscore. I think that's actually two underscores. And then, capital F, and then II, which probably refers to the fact that it takes, two integers, and then this Shazam, capital F DD, which is going to take two doubles. So in other words, inside the assembler, these are not the same function. They're different. They're called different. They've got different names. They go to different code, et cetera, et cetera. Okay, that concept of the kind of the mangled names and that notion of overloading, either having it overloaded within the language or overloaded explicitly, the language allows you to kind of create your own overloads, is a super, super important concept. And that's a wrap for this podcast. We're going to come back on the next one and talk about parameter coercion, and then all the other ones in the subsequent podcasts.